Hey fifth grade, welcome to your oceans floor and currents lecture. No more up today. It's a bit longer of a lecture because it's two whole sections in the book. It's chapter 9, pages 108 through 111. So it's the floor and current sections in the chapter. So we'll start with the ocean floor, and starting on slide 3, we'll talk about how can we see the ocean floor. So in the early 1900s, the echo sounder was invented. Sound waves were used to help provide pictures of the sea floor. So what they do is they mount the echo sounder on the bottom of a ship. What the echo sounder does is sends out sound waves, and they bounce off the sea floor and come back. And the scientists that are manning the ship can take the readings from the sound waves and then calculate the depth of the seafloor at certain points. In the 1950s and 1960s, this was used a lot, and they were able to find underwater mountain ranges, volcanoes, ridges, and trenches, and lots of different things. So we were able to map out a lot of the seafloor. There's still some stuff we don't know, or it's too deep for us to know. But all these things showed that there is movement underneath the ocean surface, that the land, the earth, that makes up the seafloor, does move, it can move, it does all sorts of things, it makes all sorts of different changes in the land. So if you flip to slide 4, that picture is a picture of a boat using an echo sounder. What it's doing is that little beam, or multiple beams in reality, sends out a bunch of the sound waves. It measures the time it takes round trip for the sound waves to return in the echo, and they get that picture of the bumpy seafloor that's there. All right, on slide 5, we'll talk about the oceanic divisions. So the ocean has 3 basic areas: the continental margins, the deep ocean basins, and the ocean ridges. Each of these have their own levels of depth and their own characteristics, their own organisms that live there, and all that kind of stuff. So our first one is continental margins. You can see in the picture on the right. So the continental margin includes the continental shelf and the continental slope. In reality, these are just extensions of the continents that we know. So, for example, North America, the continental shelf extends about 65 kilometers or 40 miles out to sea. So when you go to the beach and you step into just straight onto the beach part, that's the coast. And then the second you step into the water and go out a little bit, that is the continental shelf. The continental slope is the drop-off. So if you were to go out about 40 miles, you wouldn't be in the shallows anymore. There would be a steep drop-off into the open ocean. It's where the continent itself pretty much ends. Okay? You can see on the picture there, the continental shelf is exactly what I said, that little bit of shallow part that's covered by the breakers and all that that you can see. And the continental slope is that steep drop-off. Okay? So, let's talk about deep ocean basins. So, the deep ocean basin is pretty much any part of the open ocean. It has 2 main features: the abyssal plains and the seamounts. Abyssal plains are large, nearly flat regions of the ocean floor. In reality, they're not actually flat, they're pretty bumpy because we know sand moves all around, but they're just those open stretches where it's just seafloor and there's no big mountains, no big trenches, all that kind of stuff. On the other hand, a seamount is an undersea volcanic mountain in the ocean floor. So it is a mountain, but it's volcanic in the fact that it has magma in it. These are formed by being near either some divergent plates that pull apart, or hotspots, which are just heated portions of the crust, and magma will well up and form that volcanic mountain. Slide 8 is where we start talking about ocean ridges. These are trenches that are underwater valleys. where old ocean floor changes form. So remember when we're talking about old versus new crust, the stuff that's old is on top. It's what we walk on. New crust is into the upper mantle where it's being recycled, melted down, and then eventually some seismic event happens and it will come up again. That's the new crust. But these are old pieces of crust. They've already happened. They've been there. So when two plates converge and they come together, they can undergo subduction. And subduction is basically one plate goes underneath the other. So we have two plates here. They're just, chilling until they start to move. They start converging, and instead of just like crumbling all together, what's going to happen is one plate will go over the other plate. So it'll go like this. And all the stuff up here will be a little mountain or whatever. And then the plate that goes down will go into the mantle, be recycled, and become new crust eventually. So what happens is the one plate is forced under the other, and the floor will spread apart because of all this happening. It'll go like this, and there'll be a gap in that little spot. And magma will fill the open spaces to a certain point, and you get trenches like in the picture there. The deepest trench in the world is the Mariana Trench, and we still don't know what's the bottom of that one. It's really deep. I saw some pictures the other day that if you put Mount Everest at the bottom of the trench, it still won't reach the top of the ocean. So that's all about the ocean floor. I talk kind of fast, but it's okay. So let's go on to ocean currents. That's the next section in the book. So we have two main kinds of currents. We have surface currents and deep ocean currents. Surface currents are driven by temperature and wind. They're really kind of what you can see, like if you're on the beach. You can see the currents moving, like the high tide versus low tide sort of thing. For example, if you are on the beach all day and you see the tide changing, you might see current changing. You might see how the waves, maybe they're coming straight at you in the morning, but throughout the day they might start going diagonal. That's an example of a surface current. A deep ocean current are those that are well below the ocean surface. They are deep in the water. They're affected by water's gravity and density. Remember, gravity is the force that pulls things down to the core of the earth. And density, we know that density is a comparison of mass to volume. It's pretty much how compact the water is itself. Water's density is affected by its temperature and by its salinity, or how much salt there is. Because remember, ocean water is salt water. So when we have some cold water, like up near the Arctic Circle, this cold water is very dense and very salty. The opposite of that is warm water, let's say near the Caribbean. That is very warm. It's less dense and has less salt in it. I'll explain how that all works in a minute. So if we go to our next slide, slide 11, how does a current form? This is where we get into different temperatured waters. So water is layered. The warmer and less salty is on the top, and the colder salt is saltier on the bottom. If you think about it, when you're at the beach, if you're standing just right at the water's edge, the water's pretty warm. But if you go a little bit deeper, maybe up to your waist, it starts feeling a bit colder at your feet. It's the same exact principle. The water that is warmer is less dense, so it's on top. So currents develop when all these different layers, different temperatured waters are moving, and one moves faster than the other. Okay? So you have your warm water going like this, and your cold water going like this, but your cold water is going faster. So there's going to be a current. The whole process of how this works, there's a couple steps. So let's take some warm water that's down in the Caribbean. It's just going to start moving towards the North Pole, either pole, for example. We'll take the north. So what's going to happen is it will go all the way up to the Arctic Circle, and some of the water there will freeze, turn into a glacier or whatever it wants to do. And that'll go away. But the unfrozen water that's there, think about it. Remember back when we did the crystals with the salt and the sugar? When the water goes away, the salt stayed. So the unfrozen water that's there has more salt now. So it's more dense. What's going to happen is this dense water will sink to the bottom of the ocean. Will sink lower than the warmer water. And this dense water will flow all the way back to the equator, getting warmed along the way by the sun and all the other things, okay? So the next thing we're going to talk about after currents is the Coriolis effect. You may have heard this before, maybe on the weather they've talked about, oh, this year being affected by the Coriolis effect. So the Coriolis effect is explains how the ocean currents move. So ocean currents move due to the rotation of Earth. And ocean currents move clockwise in the northern hemisphere, so they move this way. And in the southern hemisphere, they move this way. So all the currents that are up on our coast right here will move clockwise. All the currents that are down near Argentina, for example, will move the opposite direction. Anything below the equator will move counterclockwise. And this effect is simply due to how the Earth rotates, and it's called the Coriolis effect. El Niño is another effect of some currents. So sometimes currents don't follow the normal pattern, sometimes things just get a bit wacky. And it causes really weird weather. So if for some reason the currents started flowing the opposite direction, weather would be affected too. So El Niño, or the child in Spanish, happens every 2 to 7 years, and it lasts about 18 months or 1.5 years, resulting in warmer winters, heavy rains, floods, droughts, and even tornadoes. What happens is that there are changes in the Pacific trade winds. Trade winds are just winds that blow steadily for a long period of time. They're sustained in one direction, which creates lots and lots of warm surface area towards the South American coast, which all this warm water shifts the weather patterns and can cause all those things to happen. The name comes from the fact during this effect, the El Niño effect, water is usually warmest around Christmas. And some South American fishermen were observing that, and they said, let's name this effect after Jesus, and they named it El Niño for the child. So slide 14, our last little section we gotta learn about today, is about upwelling. So upwelling is a process in which cold, deep ocean water moves to the surface. So back in our how currents form example, it's how the cold water will start rising to the top and becoming warm. It's caused by winds and aids in moving nutrients around the water for the fish. So if everything's really dense and the ocean was always freezing cold, all the nutrients and everything would stay near the bottom, and we wouldn't have any fish in the shallows that we can, fish and eat. But because of upwelling, all the nutrients can move towards the surface. They are still down deep, but they will move towards the surface, and the ecosystem will be in balance. El Niño, unfortunately, can prevent upwelling from happening because of all the winds keeping the water warm, and it's a mess. But so if upwelling doesn't occur, fish populations can die, and it overall harms ecosystem health of the ocean. Things can die. Maybe there'll be algal blooms in the wrong areas, all that kind of stuff. So I hope that all made sense. I'm sorry if I talked really fast, but you can always slow down the speed of the video. Just click the little gear in the settings and playback speed, and you can slow down the rate at which I talk. So you don't have any written homework, yay! But I do want you to just go ahead and read pages 108 through 111 to really digest this material. It was a lot. I explained it all, but the book will answer any other questions you have. You don't have any written homework again, but I do want you to check out directions for an extra credit opportunity. It's optional. You don't have to do it. It's a project. You have 3 different options. You get to pick between looking at the ocean floor in Finding Nemo, looking at a real life oceanography experiment called EV Nautilus, or you get to look at a oceanography accidental experiment from the 90s. And if you follow directions, let me know if you have any questions. But take a look at it, decide if you want to do it. It'll help your grade clearly if you do it. But no obligation. All right. Bye.